Hello students. In the last lecture, we have studied number of the reactions that are used in the asymmetric synthesis. Now let us see some more reactions from the question paper, how the reagent can be used, how the product can be synthesized, or how we can find the particular mechanism according to the product. So let us see the first reaction here. Now the first reaction, it is very well known reaction, Nouri asymmetric type of the reaction. Rhodium catalyst, rhodium complex is used. So chirophosphorus, phosphorus catalyst, chiral ligands are attached to the rhodium. So this type of the complex, rhodium complex or ruthenium complex, these type of the complex can carry out the asymmetric hydrogenation reaction in presence of this hydrogen. So hydrogen first will get bound to the complex and then it will react with the substrate material on the double bond, and the hydrogens will get delivered on the one side of the double bond. So it is asymmetric hydrogenation reaction, and accordingly we are getting the hydrogenated product here. So this type of the reaction are asked in the question paper. Only difference is that hydrogen is given and different types of the rhodium complexes are given. So it is not necessary to mechanism, it is probable mechanism is somewhat very complex, so it is not given. Only we have to predict the presence of the particular hydrogen is there and the rhodium complex is there. So we have to give the particular stereochemistry with the product and we have to give the hydrogenated product. So this is the simple Nouri hydrogenation, asymmetric hydrogenation. Now next reaction, it is the aromatic substrate is given and it is treated with this reagent. Product is not given, so we have to predict the proper product with the proper stereochemistry and also the mechanism for the reaction. So whenever possible we can give the mechanism, but if the reactions are repeated, I have skipped the mechanism for this reaction. Already we have discussed, we have studied all these reactions and their corresponding mechanism. So you can refer this other topics in which mechanism is given. Here now this compound, it is aromatic and the reagent is given silane manganese catalyst. So this is manganese complex with this heterocyclic ring system containing catalyst, and this very small amount of this catalyst is used. So it is oxidative reaction can be carried out, or oxidation is carried out in presence of sodium hypochloride, and the N-oxide compounds are used, or the tertiary amines may be used, or amine compounds are used. So here N-oxide compound is used, so that will facilitate the reaction, and this manganese metal especially it will carry out the oxidation of this double bond to corresponding epoxide which is beta oriented. So the epoxide is formed when this manganese silane complex react with the double bond. Now here aromatic system is given, so this all aromatic conjugated double bonds are present, and if we see this double bond is different from this aromatic system. So with this double bond only oxidation can be affordable. So other double bonds will remain unaffected. There is no oxidation occurs. So this complex selectively reacts with this double bond only. And we are getting the corresponding beta oriented epoxide. So oxygen will get delivered from the above side or the beta side. We are getting only one enantiomer. So pure enantiomerically pure product is obtained here. Now let us consider the third reaction. Now we can see here the acid substrate is given, alpha hydroxy acid is given. Generally this type of substrate are not given for the alkylation, but in exceptional cases other groups may be given on the acid or the ketone. We know that acid compounds are not easily enolized, but if we use this stronger base, then these compounds can be enolized. So here LDA is used, which act as the stronger base. This is the acid, alpha hydroxy acid. Second is the aldehyde compound is given. So this aldehyde does not contain any alpha hydrogen atoms. There is no alpha hydrogen atom because this is tertiary butyl group. It is present on the alpha side. So there is no possibility of abstraction of the proton, or there is no acidic hydrogen is present over this substrate. But this substrate contain the acidic hydrogen which is attached to the alpha carbon atom. So first step we have to consider here, the first reagent is given, it is acid. So on acid treatment what happens, this carbonyl group or this oxygen, this will get protonated. So electrophilicity of this aldehyde will get increased. So it becomes more electrophilic and strong electrophile. So we can write here, this aldehyde is get converted into corresponding positively charged species, and this LDA, we know that it is the strong base, it will abstract now this acidic proton. So thereby formation of the carbanion at this position, and this carbanion will get delocalized here, and lithium enolate is generated now. Now this orientation of the OH group, it is alpha oriented group, and next step to LDA, it is treatment with the isopropyl bromide compound. Now this isopropyl bromide compound acts as the electrophile in this case. So what happens, this aldehyde is also electrophile and isopropyl bromide is also an electrophile in this case. So we can write here, this may react with the isopropyl bromide, so thereby carrying out the alkylation type of reaction occurs. Now here this isopropyl group will get added on the beta side, because on alpha side there is OH group is present. So specifically this group will get added on the beta side. This is one product. Secondly, now this enolate ion may react with the aldehyde. So if it react with the aldehyde here, which is more electrophilic in nature, so we are getting the another possibility of the product. And this, as the OH group is alpha oriented, again we are getting the another group will be beta oriented. So these two possible products are formed in this reaction. So sometimes what happens, one or more product may be formed in the reaction depending upon the reagents given. Now let us consider the last reaction, fourth reaction. We can see here the substrate. Now carbonyl group, it is attached to nitrogen containing the 6-membered ring. Already we have know that this is the chiral auxiliary oxazolidinone compound. So this is the chiral substrate. This chiral substrate now first react with the dibutyl boron triplet compound, and we know that this type of the boron compound, especially they will form the Z enolate, and this Z enolate selectively it will form the syn aldol in the aldol condensation reaction. So there is the first formation of the syn enolate. So this is the syn enolate is formed. Now this syn-enolate, secondly, triethylamine compound is given, and next to this the aldehyde is given in presence of the aluminium diethyl aluminum chloride, which act as the Lewis acid catalyst. So in the next step here, it react with the aldehyde by aldol condensation. After protonation, this O minus group will get converted into OH group, and this is your chiral auxiliary. It is still attached to the substrate. Now here we are getting the syn product. This beta oriented or alpha oriented aldol is obtained here. Why we are getting the syn product? Because we have used the boron complex. So boron complex selectively generate the Z enolate, and the Z enolate selectively gives the syn aldol or the syn aldol syn compounds. So this is selective reaction, and we are getting the one diastereoisomer. So this is the one diastereoisomer. It is exists with the another enantiomer. So it is the racemic mixture. It is found to be a racemic because this is the single enantiomer of the diastereomer, and another enantiomer will be the compound in which the OH group and the R2 group. Here this is R2 and this is R group. R2 is present on the aldehyde. So these are directing on the same side. So these two enantiomer will exist with one another as to 50-50 as to racemic mixture. So single diastereomer is obtained, and that will exist as the two enantiomeric pair as the racemic mixture. So now we stop here. Thanks for the watching video.